previous video, we have seen the Kronig-Penney model, and we have also seen the condition for the wave-like solutions inside the periodic potential that is given by this particular equation, where this P is representing the barrier strength, which signifies the binding energy of electron inside the potential well, and its value is given by P is equal to MA V naught B divided by h cut square, where this V naught B, it is representing the area of potential barrier, and this alpha is such that alpha square equal to 2ME divided by h cut square. So the value of alpha, it has the information of the energy, and here the right hand side of this equation contains the information of wave vector. So if you put the value of alpha in this above condition, then you will get a relation which relates energy with the wave vector k. So from this, the value of alpha square, we can see that the value of alpha a, it is proportional to e raised power half, right? So I am assuming that this alpha a is equal to some constant c times e raised power half. So therefore, this condition for wave-like solution inside periodic potential, it becomes P sine c e raised power half, and then divided by c e raised power half plus cos c e raised power half. It is equal to cos Ka. So here you can see that this is the dispersion relation for the electron inside a periodic potential. Now let's see how this particular dispersion relation looks like in the graph. Before that, notice here that this cos Ka, it is an even function. Also, it is periodic, and its period is equal to 2 pi by A. So this means that here this energy will also have this similar sort of behavior, that is, the energy will also be an even function and it will be periodic with period equal to 2 pi by A. So we will show that this periodic representation of energy as a function of wave vector k for first few allowed bands. So here you can see, since the energy is periodic as a function of k, then therefore you can see that for a particular value of energy, there are multiple possible values of wave vector k. So this particular dispersion relation is obtained by the periodic representation in the region of first Brillouin zone, that is from minus pi by a to plus pi by a, and it is known as the periodic or repeated zone scheme. So if you notice here that in this scheme, the value of wave vector k, it is not uniquely defined, as for each value of E, there exist a number of k values. So therefore, it is convenient to use some different schemes. So here you can see an extended zone scheme. Here the dispersion curve, or basically the energy versus k in the extended zone scheme, it is shown by these solid lines, and there is certain gap between these solid lines. So this certain gap, it represents the forbidden band gap. If you see here, for the barrier strength equal to 0, this particular extended zone scheme, it reduces to the dispersion curve for a free electron. But when P is not 0, then the dispersion curve, it is not continuous, and it has a discontinuities at the zone boundaries. So here you can see that in the first Brillouin zone, that is from minus pi by a to plus pi by a, there is a discontinuity when it goes to the second Brillouin zone. The second Brillouin zone is from minus 2 pi by a to this minus pi by a, and then from pi by a to 2 pi by a. So the values of k where there is a discontinuity, this defines the boundaries of Brillouin zone. You have seen that there were discontinuities in the dispersion curve for the values of k equal to n pi by a, where n is a positive or negative integer. But also k value is equal to, since this is a wave vector, so its value is 2 pi by lambda. So if you compare this, then you will get n lambda equal to 2a. So if you remember, this is a condition for the Bragg's law of reflection for normal incidence. So this means that the zone boundaries, they are acting as a Bragg reflector for the electron. And the electron suffers Bragg reflections, which results in discontinuities in the EK curve. Now let's see the other scheme, which is known as the reduced zone scheme. Here, the EK curve in the reduced zone scheme is obtained by reducing the contents of all other zones so that it corresponds to the first Brillouin zone only. And the wave vector k belonging to in this region is known as reduced wave vector. So for barrier strength P, there was a continuous band, or basically all the energies are possible for the free electron case when P is 0, and when P is very large, so then we can see that there are discrete energy levels, as in the case of particle in a box. So till now we have seen the formation of bands. So now let's see how many numbers of wave functions are corresponding to a particular band. Now this was the example for infinitely long one-dimensional crystal. So there were certain energy allowed bands, and if you see here, inside of one particular band there was a continuous distribution of energy. So from here you can see that in this fourth band all the energies are in a continuous region. But this is the case for ideal crystal, or where there is an infinitely long one-dimensional crystal. So but in real systems we have a finite length of the crystal. So therefore let's see the number of wave function in a band, in this particular band, when the length of crystal is not infinite, it is finite. So here we are considering the length of the crystal to be L, and it is finite, such that there are n number of atoms which are separated by a distance a. So here the task is we have to determine the number of possible wave functions or states, or we can say k values per unit band for the case of finite lattice. So from the periodic boundary condition and the block function, we know that the wave function, it must be a periodic function. So this means that psi at x plus L, it should be equal to psi at x. So this means that from the blocks function, that e raised to power iota x plus L k, and this is modulated by u k x plus a L, it must be equal to the plane wave e raised to power iota kx and then u k of x. So also we know that this modulation function, this should be also periodic. So this means that uk at x plus L, it must be equal to uk at x. So this means that e raised to power iota k x plus L, it should be equal to e raised to power iota kx, or e raised to power iota kl, it must be equal to 1. Now I can write 1 as e raised to power iota 2n pi. So this implies that the value of k allowed are equal to 2n pi by L, where n can take values positive and negative integers. So therefore the possible values of k is equal to plus minus 2 pi by L, or plus minus 4 pi by L, and similarly so on. So as you have seen that in the case of infinite lattice, these k values were infinite, but in case when the crystal becomes finite, there were only certain values of k which are allowed, and we have to find these number of k values per unit band. So from this equation number 1, we can relate number of k values with the value of k as KL divided by 2 pi, right? And therefore the value of dn is equal to L divided by 2 pi and then dk. So this value dn, it represents the number of possible wave functions in the range dk. Now if you remember, the first Brillouin zone, it extends from minus pi by a to plus pi by a, where this a is the length of the primitive cell. And now if this n is equal to the number of primitive cells, then a must be equal to L divided by n. Also you can see that the maximum value of k for the first Brillouin zone is pi by a, and from here you can substitute the value of a, which is equal to L by n, so this will become by n and then this L. So this is the value of k max. Now the maximum value of k wave vector is equal to pi by a in the first Brillouin zone, and you can substitute the value of a is equal to L by n. So this becomes the maximum value of k will become pi n divided by L. So this means that this particular series of allowed k values, it will go from plus minus 2 pi by L to all the way up to plus minus pi n by L. So if you apply the reasoning, then you will get that there will be n such values of k which are allowed. So this means that in the first Brillouin zone, the allowed values of k is equal to n. Hence, the total number of possible states in any energy bands is equal to the number of primitive unit cell n. Now, since each band can occupy a maximum of 2 electrons, so therefore each band can now accommodate a maximum of 2n electrons. Now let's see the velocity of electron inside this periodic potential. So as we remember, according to the wave mechanical theory, the particle moving with a velocity v, it is equivalent to a wave packet moving with a group velocity Vg equal to d omega by dk. So this represents the group velocity with which the wave packet moves, or it is equal to the velocity with which the energy is transported. Now, as energy E is given by h cut omega and the momentum P is given by h cut k, so you can relate the group velocity or the velocity of electron v equal to Vg as 1 divided by h cut dE by dk. So this means that the velocity of the electron, it is directly proportional to the slope of the dispersion curve. Now for a free particle, the energy, we have seen that from the free electron theory that this energy was equal to h cut square k square divided by 2m, and we have seen that the dispersion relations forms a parabola like this, and which is centered at k equal to 0. So the slope of this particular parabola will give you the proportionality with velocity. So therefore the velocity of electron, free electron, will be equal to 1 divided by h cut, and then you will differentiate this with respect to k, then you will get h cut square k divided by m, so which is equal to h cut k divided by m, and as we know that h cut k is equal to momentum p divided by m. So for a free particle, the velocity is equal to p by m, where p is the momentum of the electron. So this was the case for the free electron, where the energy is proportional to the k square. But for the periodic potential, we have seen that the dispersion relation is not that simple. We have seen that it was like P sine c e raised to power half, and then e raised to power half, there was a c here, plus cos c e raised to power half, it is equal to cos Ka. So here the relationship between energy and wave vector k is not as direct as in the case of the free particle. Therefore, E is generally not proportional to k vector, and you can see that the slope of Ek curve is not constant, but it is changing with respect to k. For the periodic potential case, we will show the graph of this velocity of electron as a function of wave vector k in a minute. But before that, let's talk about the effective mass of electron when it is traveling inside a periodic potential. Now let's consider a case when we apply an external field E on the motion of the electrons, which is present on the first Brillouin zone. And we are assuming that there is only one electron in this Brillouin zone so that it doesn't violate Pauli exclusion principle. We are assuming that this particular electric field, it is acted for a time of dt. So the increase in the energy of the electron will be given by dE is equal to E and then electric field E dx, where dx is the distance which this electron E moves in this particular dt time, and this will be equal to E then velocity times the time. Now as you remember, the velocity of electron is equal to 1 divided by h cut, then the slope of the dispersion curve, that is dE by dk. So we will substitute the value of V here. So this means dE is now equal to E and then electric field E divided by h cut dE by dk and dt. So here this dE, it can be written as dE by dk times dk, which is equal to electronic charge and then electric field by h cut dt and then dE by dk. So this implies that this dk by dt is equal to E and then electric field divided by h cut. So this equation tells how the wave vector for the electron, it evolves in time when the electron is placed in an external electric field. Now if I multiply h cut on both sides, so then this will become d h cut k by dt is equal to E and electric field. And if you remember, this h cut k is nothing but the momentum p. So the rate of change of momentum is equal to E and then electric field, and which is equal to the force according to the Newton's second law. Here this P represents the crystal's momentum. So therefore we can conclude that the rate of change of crystal's momentum is equal to the impressed at force, that is E and then electric field. So therefore it is analogous to Newton's second law for an electron in the periodic lattice. Now as we have got the velocity of electron in the periodic lattice, from this we can calculate the acceleration for this electron. Now since velocity is equal to 1 divided by h cut derivative of energy with respect to wave vector k, so therefore acceleration will be equal to dv by dt, which will be equal to 1 divided by h cut del square E by del t and then del k. So this can be written as 1 divided by h cut del square E by del square k times del square k by del t. And we have calculated this del k by del t as 1 divided by h cut E and then this electric field. So therefore the acceleration for the electron will be given by 1 divided by h cut square E and then electric field E times del square E by del k del square k. Now for free electron, the energy was related to wave vector as k square h square divided by 2m. So if you differentiate energy with k twice, so you will get d square e by k square equal to h square divided by m. So therefore, the acceleration for free electron will be equal to E and then electric field E h square times h square divided by m. So the acceleration for free electron will be equal to E electric field divided by m. Now if you compare these two accelerations for the free electron and the electron in the periodic potential, then you can notice that this particular quantity is representing the effective mass in case of periodic potential. So in periodic potential, the mass can be given by h square divided by d square e by dk square. So the comparison of these two equations, it gives an interesting result of the band theory, that an electron moving in a crystal, it has an effective mass m star, which is given by h square divided by the double derivative of dispersion curve. So this implies that this effective mass is not constant value. And it depends on the shape of E and K curve. Now it is generally very convenient to introduce a factor Fk, which is a measure of these two masses, and this quantity is equal to m divided by h square d square E by dk square. This quantity Fk, it is a measure of the extent up to which the electron in the K state behaves as a free electron, and if Fk value is equal to 1, so the electron behaves totally as a free electron, and if Fk value is less than 1, so then in that case effective mass is greater than the usual mass of electron m, and in that case the electron behaves as a heavy particle inside the periodic potential. Now let's see the dispersion curve for the particle in a periodic potential and the derivative of it, which represents the velocity of electron, and the double derivative of it, which represents the effective mass. Here you can see that in the reduced Joule scheme, where the wave vector k is in between minus pi by a to plus pi by a, so you can see the dispersion curve is shown in here by this blue curve. And if you take the derivative of it, so you will get that the derivative of this is not a constant, but it is also a function. So this means that the velocity of electron, it is not a constant inside a periodic potential, and it depends on the wave vector k. Here you can see that at the center of zone, the velocity of electron is 0, since v is equal to 1 divided by h cut dE by dk. At the center of the zone, the derivative of this first dispersion curve, it is 0, so the velocity is 0 at zone center. While as you move away from the zone center, the slope of this dispersion curve, it is increasing, so the velocity will be increasing to a point where it attains a maximum. This point is known as an inflation point, after which the velocity of electron, it is decreasing, and it decreases to 0 at the zone boundary, where the velocity is again 0. Therefore, you can conclude that the velocity of electron is 0 at the zone center and at the zone boundary. Or you can say that the velocity of electron is 0 at the top and bottom of the energy band. Now at this inflation point k naught, this velocity of electron in the periodic lattice, it attains a maximum velocity which is equal to the velocity of free electron v naught, and beyond this inflation point the velocity decreases with increase in energy, which is a completely different phenomena from the behavior of a free electron. Since in the free electron theory, as we increase the energy, the velocity of electron it also increases. But here in the band picture, you can see that there is an interesting thing which is coming into the picture, that as we are increasing energy, after a certain point, the velocity of electron it is decreasing. Now let's see the double derivative curve of dispersion relation, which represent the shape of EK curve. Now here you can see that till this inflation point K naught, the effective mass it is a positive value. While after this inflation point, which is on the both side of this center, the effective mass it is becoming negative value. So therefore, here if you see that in the band picture, this is the lower half of the band, and in this band the velocity of electron it is behaving as a similar as a free electron, but above this band the velocity of electron it is decreasing with increasing energy. Also the effective mass in this lower region of the band it is positive, while when the energy it is exceeding this particular inflation point, then the effective mass is also becoming negative. So this is a very completely different thing happening in the case of band picture. Now this concept of negative effective mass it can be understood in terms of Bragg reflection. So as we know that close to this zone boundary, the electron suffers a Bragg reflection. So a force, if a force is applied it in one direction, then after the reflection, it will lead to a gain in momentum in the opposite direction, which results in the negative effective mass. So the concept of effective mass has the physical significance, as it provides satisfactory description of the charge carrier in crystal. As in the case of semiconductors, the positive mass particles are known as holes, which act as a positive charge carriers to produce conduction. Now let's see the differences between metal, insulators and semiconductors based on this band theory of solids. Now in order to distinguish between metals, insulator and semiconductors, we are going to consider this energy band which is filled with electrons up to a certain energy value, which is given by the inflation point, this K value, K1. So the electrons are only in between this range. Now, now we want to know how many electrons are there in between these two limits of K vector. So that is N effective. This N effective represents the number of free electrons present in the band. This is the number of electrons which will be responsible for the conductivity. Now if you remember, we have defined this quantity Fk, which was the ratio of the mass of electron, free electron, and the effective mass of electron, which represent the extent up to which the electron in the K state behaves as a free electron, hence participate in the electric conduction. Thus therefore, in order to determine the total effective number of free electrons in this energy band, we have to sum up over all the possible Fk values corresponding to various occupied energy levels present in this band. So therefore, N effective it must be equal to the summation of all Fk's. Now also if you remember, we have calculated the number of electrons inside a particular range of dk as equal to L divided by 2 pi times dk. This was for the crystal of length L, and since each state is occupied by a maximum of 2 electrons, the effective number of free electrons present in the band between minus k1 to plus k1, it becomes N effective is equal to 2 times L divided by 2 pi, and then from minus k to plus k 1, Fk dk. So this is the number of free electrons present in this band, which are responsible for conductivity. So if you simplify this, then this 2 gets cancelled with this, and you will be left with L divided by pi, and then integration of Fk from minus K1 to plus K1. And you can use the value of Fk, which was equal to m divided by h cut square d square e by dk square. So you can put this value here. So you will get L divided by pi times m divided by h cut square, and then the integration of this will give you the first derivative of dispersion curve from minus k1 to plus k1, and you can write it as twice L m divided by pi h cut square times first derivative of dispersion curve at k equal to k1. So this is the effective number of electrons, or the number of electrons which will be responsible for conduction inside this particular band. And if you notice here that this first derivative is related with the velocity of electron. So let's see the conclusions. So first of all, as we have seen that at the zone boundary and at the zone center, the velocity was equal to 0 at k equal to 0 and plus minus pi by a. So this represent top and bottom of energy band. So this means that the number of electrons which are responsible for conduction, they will be 0 at top and bottom of the band. So this means that in case of completely filled band, the N effective will be 0 for completely filled bands. Now if you see that the velocity of this electron inside the periodic potential, it is increasing from the bottom of this band to a maximum value here at the inflation point k1, and after that it is decreasing. So the effective number of electrons, it is maximum at the inflation point, that is at k1. So therefore the band is filled up completely at the point of inflation. So now let us distinguish different types of solids based on the effective number of electrons which are responsible for conduction. So the first type of solids will be insulators. Now insulators are the solids having a certain number of energy bands completely filled and all other bands are completely empty. Now if you remember from the Kronig-Penney model, this was the band structure. They were the energy allowed bands, and inside each band there can be an effective number of electrons. So insulators are solids having a certain number of energy bands which are completely filled. So let's say these lower bands, they are completely filled and there is no space for any other electrons, and all the rest of all these bands, they are completely empty. This is the situation when the temperature of the system is at 0 Kelvin. But when these electrons, they get some thermal energy, so these electrons may get jumped to the higher excited band, and they can correspond to conduction. Now the number of such free electrons which are thermally excited, they depends on the value of forbidden energy gap. This is Eg. This lower level, which is completely filled, is known as valence band, and the just above band is known as conduction band. Now any thermally excited electron, it may jump to conduction band if it gets sufficiently high energy to overcome this band gap. So in that case, it can become a conductor. So the second type of solids are conductors. So conductors are the solids having partially filled energy bands and they have a metallic character. So this means that their conduction band they are partially filled. So inside a conductor this conduction band is partially filled so that the electrons in the conduction band they can contribute to the conductivity. Now the third type of materials are semiconductors. Semiconductors are the solids which are insulators at temperature T equal to 0 Kelvin. And if this energy band gap Eg is very small, then the number of thermally excited electrons it becomes very high even at some ordinary temperature, and the material it behaves as a conductor. So that's why these are known as semiconductors. In the case of semiconductors, the band gap is about 1 electron volt. So at absolute zero, they behave as insulators. While if they get sufficient thermal energy to overcome this band gap, they can contribute to conduction. So therefore, we can say that all intrinsic semiconductors are insulators at absolute zero, and all insulators they may behave as semiconductors if the temperature is sufficiently higher than this 0 Kelvin. Now it is also important to note that the conductivity of semiconductors it increases with temperatures because the number of conduction band electrons it is increasing with temperature, while in case of metals the conductivity decreases with increasing temperature. This is because as temperature increased, more and more phonons are excited to higher energy levels, which may scatter conduction electrons, and therefore it may reduce their mobility. We have seen that how band theory was able to distinguish between insulators, conductors, and semiconductors. So this was a very great achievement of band theory and Kronig-Penney model, which was very helpful in understanding the semiconductor properties. So this is it for this band theory of solids. Thank you for watching this video. We will meet next time with some other interesting topics.